Anybody still need a copy of the syllabus tonight? This is- Okay, any questions on the homework we did last time? Yeah,
Number 21, it was like E squared or something. It was some obscure way to do a limit that frankly I forgot.
okay. I think I know what you're looking at, yeah.
I like have it in here somewhere.
Yeah, let's do that one. That's a hard one. I was thinking about that one last time. and Didn't have time for it. All right, so here's an example of evaluating a limit of a sequence. Suppose you have this sequence of numbers n plus one over n plus three to the nth power. No, it's n plus three over n plus one. What is the limit of that sequence? So this is the list of numbers. You put in n equals one and you get 4 over 2 is to the 1 is 2. Then you put in 2 and you get 2 plus 3 is 5 over 3 squared. So that's 25 ninths. Put in 3, 6 over 4 is 3 halves cubed is 27 eighths. Oh, that's an obscure list of numbers. I wonder what its limit is. What are those numbers settling down closer and closer to, or are they settling down closer and closer to something? So we know what that means. The limit of a sequence means the limit as n goes to infinity of the nth term. That's the limit by definition, right? Well, now what's the nth term? We're lucky we got it in this form. It's whatever's in the parentheses. And the limit as n goes to infinity of n plus 3 over n plus 1 to the n. And now how do you take the limit when n is in the power and also in the base here? What you do, what I like to do at least, is to rewrite it. Write it as e to the natural log of n plus 3 over n plus 1 to the nth, right? E and ln undo each other, so it's the same thing, just by algebra. But now you can pull the exponent down. This is the limit as n goes to infinity of e to the n natural log n plus 3 over n minus 1. Okay. Then you gotta rewrite this in a clever way. The idea is that it's still hard to tell what this is doing from the beginning. The reason I do this is that this is approaching 1, but this is approaching infinity. What is 1 to the infinity? We don't know. It's an indeterminate form. If these are not approaching 1 fast enough, then as this goes to infinity, this might approach infinity. Or it might approach 0 if these are a little less than 1 and not going to 1 fast enough, then the nth power might go to 0. Like it's higher and higher powers of like 0.9 tend more and more towards 0. Or it might be that this approaches 1 pretty fast and the limit is 1, right? So we can find out anything in between then. Let's see what we get. But when we have an indeterminate form, what do we usually use to evaluate the limit? Yeah, L'Hopital's rule. There we go. So I'm going to do this. I'm going to take this as e to the limit. N goes to infinity of n times natural log n plus 3 over n plus 1. And to use L'Hopital's rule, I need to rewrite this as a quotient. I was just trying to think what's the best way to do that. I suppose we write this as e to the limit of ln of n plus three over n plus one over one over n. So that's the same thing, but now it's written as a quotient. And in this quotient, this is limit n goes to infinity. One over n is approaching zero, right? One over bigger and bigger numbers approaches zero. N plus three over n plus one as n goes to infinity, we know from the closest to polynomials approaches one. And ln of numbers getting closer and closer to one are gonna approach zero. So these arrows mean this is the limit. If I just took the top would be zero. If the limit I just took the bottom would be zero. If it's zero over zero, then I can apply L'Hopital's rule, right? If it's zero over zero or infinity over infinity, that's when it applies. Don't apply it to something that has a finite limit, sometimes it's the wrong answer. L'Hopital says that, you can now write that as limit n goes to infinity of the derivative of the top over the derivative of the bottom. So derivative of the top, I have to figure out, right? Recall the derivative ln u with respect to x. So prime means derivative with respect to x. Is derivative ln u with respect to u, one over u times the prime. We could write that out in detail if you want. Or you could write it this way. Derivative ln u with respect to x is d ln u du dx by the chain rule, right? So this is u prime. And derivative ln u with u as the variable is one over u. So that's where I got that from. So this is one over n plus three over n plus one is n plus one over n plus three. And then I need a derivative of n plus three over n plus one. And down here, derivative minus one over n, one over n is minus one over n squared. Derivative n of the minus one is minus one, n to the minus two. We've got that, and now we need the derivative n plus three over n plus one. Remember the quotient rule? That's always the hardest one. I have trouble remembering that one. I told a few of you this one already. If you have a quotient, you can put it to song, right? If you want to do this, usually use like one way to do derivatives with a d. You'll see this in higher mathematics sometimes. So d of high over ho is what? It's ho d high. It's high d ho over ho ho. There we go. So that's my 7/4 version. Off the word we go. Anyway, but and then really it's f over g prime is gf prime minus fg prime over g squared is what that says. And so there for derivative n plus three over n plus one, I can do over on the side and say n plus three over n plus one prime is g, the bottom, n plus one times the top derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So it's apparently n minus n cancels. And you got 1 minus 3 is minus 2 over n plus 1 squared. Okay, so we can write it like that. Okay, it's easy to make a mistake at that step. All right, so this is e to the limit, n goes to infinity of, put this minus 1 over n squared here still. And on top, I've got n plus 1 over n plus 3 times minus 2 over n plus 1 squared. Is that what, minus 2 over n plus 1, n plus 3. Slide. Multiply that times this, and one of the n plus 1's canceled. And I got minus 2 over n plus 3, n plus 1. Okay, now the minuses cancel. And I take top times bottom. Over the middle times the middle, I've got n squared times 2 over n plus 1, n plus 3. Now I've got it, it's a nice quotient I can evaluate. What's the limit as n goes to infinity of 2n squared over n plus 1, n plus 3? Let's write it out. It's e to the limit n goes to infinity of 2n squared over n squared plus 4n plus 3. And you recall for limit of quotient of polynomials, it goes by the dominant terms. If they're the same power, then the limit is the quotient of the bottom term. Top term is 2 to 1. This is e to the 2. There's the limit. The reason I can pull the limit up in the exponent here is that the exponential function is a continuous function. So if I get a limit out of this, and then it justifies that I can put the limit inside the exponential. Well, that's a tricky one. You have a function of n to the nth power. Try writing e to the ln, and sometimes it helps you rewrite it as a quotient. Any other ones? Yeah, that was the hardest one. Thank you for doing the homework. All right. Seems like we have more people than last time. Some of you out since last time, maybe. Maybe you got it. It's better. It's really hard to read. Well, we did sequences last time. This is the boring part of the course. I'm sorry to tell you. We want to do more with sequences this time. We'll talk first about monotone sequences. Really boring. Anyway, we'll say that if for each n greater than or equal to 1, you have that an is greater, an plus 1 is greater than or equal to an, then the sequence of an's, and recall from last time, that's just notation for the infinite list of numbers, A1, A2, A3, and on forever. Then this one is said to be increasing. This is kind of awkward because the function can be each term next equal to the previous one. It's still increasing. I mean, you can have sequence 1, 1, 1, 1. According to that definition, it's increasing. Some books give a little different definition where it has to actually be greater. This book is a classic book. It's been around for over 40 years with different editions. And so I'm not going to argue with it. I just think it's kind of odd because you think of increasing stock market goes up, it's stable, right? But anyway, what they do to differentiate that is we'll say, or it's strictly increasing. If this happens, if an plus 1 is strictly greater than an, then the sequence and is strictly increasing. Then similarly for decreasing, I'm so sorry, that's so boring, especially at night. If for n greater than or equal to 1, an plus 1 is less than or equal to an, then the sequence of numbers is decreasing. Or if an plus 1 is strictly less than an, it is strictly decreasing. So that defines all those terms. And then finally, yeah, it is either increasing or decreasing. I'm tired of writing already. It is said to be monotone. If it is strictly increasing or strictly decreasing, then it is strictly monotone. So you hear those terms, just want to know what they mean. Point of this is to put rigor into results that come up. And one of them is this. What is the result? This definition. If a sequence is strictly is increasing and bounded above. What does bounded above mean?
Horizontal asymptote?
That's gonna be the conclusion of the theorem. You're going past that, yeah. Just if it's bounded above. It means that there's some number that never gets bigger than. So bounded above means, each AN is less than or equal to some number M. So it's maximum possible. Then it has a limit. There's your asymptote, that's the conclusion. And in particular, that limit L is less than or equal to M. And furthermore, if it is decreasing, which includes strictly decreasing, right? If it is decreasing and bounded above, bounded below, excuse me, bounded below, meaning that each AN is bigger than or equal to some number M for some M, then it has a limit also. That limit L is bigger than or equal to M. Right? And the idea is all that is a lot of stuff that's hard to remember, but the idea is this: you have the sequence which you can mark off as discrete points, whatever we call that. And if we have a sequence of numbers, AN written this way, and if you want, you can put this on here. N equals 1 to infinity is assumed if you don't write this in there. Meaning the list, A1, A2, A3, like until some of this tortoise going forward. The list of numbers, their position is or something. We can plot it. We can plot the point 1, A1, just thinking like this is the function A of 1, 1 with A of 1, 2 with A of 2, right? 3 with A of 3, and so on. It really is a discrete function. You could write it this notation. Nobody does because who wants to write 2 extra parentheses, but and so on. And the idea is that if these dots are settling down to a line y equals L, so that you have a limit, or excuse me, if these things are getting low or decreasing, getting lower and lower, but never reaching this number down here, M, then there's some line here that they must be approaching. It could be M, but it could be they slow down towards something else up here. That's the latter case there. And the former case, where it's bounded above, is you might have an increasing sequence, so the points are going up. There's 1A1, 2A2, 3A3, etc. And they're increasing, so they don't come back down, but they never reach some line up here, as you get dotted, y equals M. Then there's some line here, y equals L, that they're getting closer and closer to that's its limit. in calculus one, you would call this an asymptote or a continuous function. For here, we just call it the limit of the sequence. Okay, so that's the concept. If you remember this, you remember that. So it's useful then to be able to say if a sequence is increasing or decreasing, because, you know, if you can do that and show the numbers never get more than so high, then you know it has a limit that's less than or equal to that. And so you want to prove a limit. Sometimes you maybe can't figure what it is, but you can prove it exists, and that could be useful enough for a lot of cases. Oh, yeah. Note, sometimes these things may jiggle around and then increase forever. So it's useful to say, this theorem also applies. Easier to draw the picture like that and then do this exception afterwards. Do sequences that are eventually increasing or decreasing. You can probably guess what that word means. Eventually increasing or eventually decreasing means that if you throw out a finite number of terms, then it's always increasing or decreasing. So these theorems, you can jump up and down for a while as long as they eventually, after some finite point, start all decreasing towards and are bounded below. And they can jump over the bound as long as if far past some finite point, they're going down towards, going down and above the line. Okay.
What's an example of a function like that?
Suppose I had an equals natural log n squared or something. Squared over n. This one, if we'll actually maybe run into one of these in the homework, but natural log at 1. Okay, so I'd have to calculate this to be sure. But if this increases a little faster, I think if 1 is nearby. And so when n equals 1, this is equal to 0 because it's 0 over 1. So it goes to this point here at 1. And then when n equals 1, when n equals 2, you've got ln of 2 squared. Is a positive number, so it's up here. And divided by n is still positive, so it's up here. But as n gets larger and larger, what happens? N goes to infinity faster than natural log squared, and so these eventually start coming down like that. So that would be a function like that, one that starts off with the top function driving it, but eventually is overpowered by the bottom function. Or here's another one. This one we discussed last time. Suppose I put x to the 10th over n to the 10th over e to the n, right? N to the 10th takes off very fast, and so the numbers go up for a while, while e to the n does not take off so fast, but eventually this is how it grows. The limit is 0, but it initially takes off very fast, so the function goes up like this, real steep, and then comes back down as the exponential overpowers it. So that'd be an eventually decreasing sequence, those kind of things. This one, this one. Okay, so these kind of sequences, you say past this point, now they're decreasing and they're bounded above by 0, so they're limit 0 in these two cases. Get dirty fast. So we want to find out when do these things, how can we prove these things are increasing or decreasing so that we know that they have a limit? This is for the mathematicians here, the engineers all want to know what the limit is. There's three different methods in here, and the first one is use the difference of successive terms. An plus 1 minus an to show that the following are strictly monotone, strictly increasing or decreasing. That's one way to compare, to look at the difference of successive terms. So we could do this one. The sequence n over 4n minus 1. When they were like, write it like that, that's an, and use a little algebra in here, say an plus 1 minus an. Again, this is like a of n plus 1. How do you calculate a function at n plus 1? You just, everywhere you see n in here, you replace it with parentheses and put n plus 1 in. So n plus 1 is parentheses over 4 parentheses minus 1. Put in n plus 1. There's an plus 1. And then you subtract it from what you see, n over 4n plus minus 1. 4n minus 1. Oh, 4n plus 1. I give it minus 1. Over n, that's 4n minus 1. Now, how do you subtract those things, right? It's algebra. You just have to put them over a common denominator. This is n plus 1 over 4n plus 3 minus n over 4n minus 1. So you have to multiply this one top and bottom by 4n minus 1. To get the same denominator. You can multiply this one top and bottom by 4n plus 3, the other denominator. Now that they have a common denominator, you can subtract them. Let's see, this one looks like 4n squared plus 4n minus n is plus 3n. And then minus 1. This one looks like 4n squared plus 3n, nothing. So this one minus that one gives minus 1 over 4n plus 3. 4n minus 1. Well, for n greater than or equal to 1, the bottom is positive, right? And the top is negative. So this is less than 0. That's less than 0. And you say, all right, an plus 1 minus an is negative. That says that it's since an plus 1 minus an is less than 0. An plus 1 is less than an. I just add an to each side, but that's the definition of strictly decreasing, right? Yeah, each term is less than its predecessor. So this one you conclude is strictly decreasing by an algebra. Now, a second way to do these is take the ratio of successive terms. Maybe I should do one more of those. Should I do one more?
But aren't there some cases where it would be positive?
Yeah, then you said strictly increasing.
I got a question. What's the difference between strictly increasing and just increasing?
Yeah, strictly increasing means that each an plus 1 is strictly greater than its predecessor. That's strict. Increasing means that each an plus 1 is greater than or equal to. So,
Oh, okay.
yeah, so this is increasing. This is strictly increasing. And like I say, in some other books, they just call this increasing, and it's a little confusing on this topic, but
So if like an plus one minus an is equal to zero,
yeah, then it's both increasing and decreasing technically, yeah. According to this
That's a fun
definition,
one.
yeah. Yeah, and it doesn't, that's why I think some of the other books changed it. But all the theorems work with these definitions.
So do we have to identify whether we're using it, if it's a geometric, like,
We're getting to that,
Not
yeah.
whether-
Eventually we do, yeah, yeah.
because that's gonna be the common difference or common ratio.
Yeah, yeah.
Okay.
Yeah. Okay, maybe we should do one more, huh? Let's do this one. This is number 5. This is on your homework list there. Suppose I have the sequence, that one's like your homework, you've got a step different one though. Suppose I have the sequence n minus 2 to the n. Again, n equals 1 to infinity. That's strictly increasing, so that's either strictly increasing or decreasing, which one it is. So this is the nth term an, and again, if we do different, take this, in terms, we say n plus 1 minus an is for an plus 1, we replace n with parentheses. Put in n plus 1, so it's n plus 1 minus 2 to the n plus 1. Because it's just a function, it's a discrete function, a of n, right? And then minus an, you just copy what you see. And now you want to subtract these and see what you come up with. Oh, n minus n, these are going to cancel, that's nice. So I've got 1 plus 2 to the n plus 1, excuse me, minus 2 to the n plus 1 is minus 2 times 2 to the n. That's this one. Plus 2 to the n. What have I got? Minus 2 to the n plus 1 of them is minus 2 to the n. So this is 1 minus 2 to the n. This is always less than 0 for n greater than or equal to 1, right? It's strictly less than 0 because 2 to the n is 2 or bigger. So since this is less than 0, it follows by adding a n to each side that an plus 1 is less than an, which is the definition of decreasing again, strictly decreasing. That's what you do in a lot of algebra. But now if you can show it's bounded below, then you show it has a limit. This one does not, right? Because it's 2 to the n just gets more and more negative without bound. All right, the next one is ratio of successive terms. And we'll use an plus 1 divided by an to show the strict increasing or decreasing. Abbreviate. And suppose we did something like this. N times e to the minus n. N going from 1 to infinity. Nice, an. So n plus 1 over an. You replace n by parentheses. And put in n plus 1, that's an plus 1. Then down here, you just leave it like it is, n e to the minus n. And let's see, this one is e to the minus n times e to the minus 1. And then we can use some algebra to cancel the e to the minus n's. And this thing comes out to be e to the minus 1 is 1 over e. So 1 over e multiplies n plus 1 over n. And now it's, when you had successive terms you wanted to compare with zero, you wanted to show it's less than zero, greater than zero, to show that it was decreasing or increasing. This one, you want to show it's less than or greater than one. If n is one, then this ratio is two. And if n is bigger than one, this is smaller, so this is less than or equal to two. And this is approximately 1/2.7. So this ratio is actually strictly less than or equal to one, right? A number less than or equal to two divided by a number at least as big as 2.7. So that's strictly less than one. Well, if an plus one over an is strictly less than one with positive terms, you have to use positive terms for this test. Positive terms an, which is an is called the nth term. Then you multiply through by an and say that an plus one is less than an, and that shows again that it's strictly decreasing. But if you get an plus one greater than an, then by definition it's increasing. Strictly increasing. We should do this one. This is a lemon off your homework. Suppose we have this, the sequence whose terms are n to the n over n factorial, n running from one to infinity. How about that? What do we do? This one, we're gonna see similar things later in the semester, actually. When you see n factorials and n powers, a common thing to do, the common test is not to do the subtraction the first time, but to do a ratio, because things tend to cancel. So when you see these, think of doing a ratio like we're doing here. Cancel. We'll say this is an here. And if we take the ratio an plus one to an, then an is copy what's there into the n over n factorial. But up here, we'll put parentheses to the parentheses over parentheses factorial and put n plus one in. Remember what factorial means? N factorial means n times n minus one times n minus two times n minus three, all the way down to 2 times 1. The numbers 1 through n multiplied together is n factorial. We're gonna need those a lot this semester, actually. So now it's a quotient, so you can rewrite as top times bottom over middle times middle. We can write that as n plus 1 to the n plus 1 times n factorial over into the n times n plus 1 factorial. Now here's a trick here. N plus 1 factorial is the numbers 1 through n plus 1 multiplied together, right? N plus 1, n minus 1, all the way down to 2 times 1. But wait a minute, these numbers are n factorial, so n plus 1 factorial could be rewritten as n plus 1 times n factorial. Now I can get something to cancel. So this will be n plus 1. Oh, and this one I can also write as n plus 1 to the n times n plus 1. It's this one, all times n factorial. So I rewrite the top by factoring this one into like this. And I'll rewrite the bottom, n plus 1 factorial, as n plus 1 times n factorial. How about that? And now I see some things will cancel. N factorial cancels n factorial, n plus 1 cancels n plus 1. This is actually n plus 1 over n. So the n is left, right? So what about that? The object in these ratios is to show that this is greater than 1 or less than 1. Well, n plus 1 is always greater than n for n at least 1. And you take the nth power of that, that's greater than 1. Right? Because the top is bigger than the bottom. And the nth power is also greater than 1, right? So this is strictly greater than 1. that shows by multiplication by an, again for positive terms, an plus one is greater than an, but that by definition is strictly increasing. Each term is bigger than its predecessor. So that's the second method, is two ratios of common terms. Then the last method is returning calculus one, and then you say, well, a function was increasing if its derivative was positive, right? Well, what you can do is sometimes find a function that goes through these points and check its derivative, and that's the last method here. So example 3 is use differentiation or use the derivative. Differentiation means taking the derivative. To show that this thing is strictly increasing or strictly decreasing. Strictly increasing or strictly decreasing. And suppose I have this one, this is 17. N over 2n plus 1. And running from 1 to infinity. What you do is you instead consider the corresponding continuous function x over 2x plus 1. And compute it, if you want to see if a function is increasing or decreasing, what we used to do in calculus 1 was take its derivative. The derivative, where the derivative is positive, it's increasing, where the derivative is negative, it's decreasing, right? We remember that. So by calculus 1, we consider the derivative, x over 2x plus 1. Derivative, we go to the dreaded quotient rule and say, oh, it's g bottom, f over g, times f prime is 1, minus f x times g prime, the derivative of the bottom is 2, all over g squared, x plus 1. Well, now 2x minus 2x, this cancels this. And I just got 1 over 2x plus 1 squared. Oh, look, it's 1 over a square. It's positive. Right? This is positive. This is positive. So it's positive. Oh, the derivative is positive. So this function is increasing for all x, where this isn't 0. Increasing, well, strictly increasing. Let's say for a function, derivative positive means increasing, and that makes more sense. Increasing for x greater than or equal to -1/2, actually. So it includes all whole numbers, all positive numbers. So I'd say whole includes 0. Anyway, so x greater than, so therefore the sequence is also is strictly increasing. The function's increasing by the definition of this f of x. That's the trouble. That's why I don't like this definition. The function is increasing if for each x1 and x2, f of x2, if x2 is greater than x1, then f of x2 is bigger than f of x1. So there it's actually going up. You want that flat function is increasing, but the discrete case is finding it that way. Anyway, so the function is increasing means that each f of x2 is greater than f of x1, and that means the sequence is strictly increasing. So the sequence strictly increases. That's really pretty much the whole section that I want you to be able to do. It's those 3 tests.
So the -1/2 came from setting the bottom to 0 or equal to 0.
Oh, yeah, from setting this equal to 0. It's a square, so it's never negative, but it's equal to 0 at one point, x equals -1/2. So if you pick x greater than -1/2 or x less than -1/2, then it's positive over positive, it's an increasing function. Even if you can't graph it, with your graphing calculator, you could graph it and figure it out. But yeah, it's always positive over positive, except at one point it's not defined. And we only need it for, since x is replacing n, we only need it for n greater n greater than or equal to 1. And that includes that. Oh, and then I wanted to make an announcement also. If anybody's interested in any clubs, in joining any clubs, they're gonna be tabled over at Howell Hall Atrium. Howell Hall's the science building just to the northeast here. It's the next building right across this little street here. Show up in Howell Hall between 11 and 1 tomorrow. You can come in then. All the clubs from all the different places are gonna be there. I'm gonna take names for the astronomy club. We had a Pegasus Astronomy Club here for years and years. Due to COVID, we kind of shut down. I'm gonna see if we get enough students to run such a club. It's always student run. But I'll make some signatures at the table or names at the table. I don't need your signature. Or somebody else will. And maybe we'll get the club started, but there's lots of others. I think there's a chemistry club and a physics club and all sorts of other things. So maybe you want to join that. I think there's also food. When I was a graduate student, I always went to things that had food. Maybe you'll want to go too. All right, now we'll do something slightly more interesting. The good news is that monotone stuff is the most boring stuff of the semester. And it will gradually get better. The last part will be real fun because there'll be pictures in 3D. Next topic for the course then is series. We need the sequences first, but this is actually more important. But in order to define these, we need the sequences first. So we'll simply say this, an expression written in either form, sum, sigma, n equals 1 to infinity of an, also written this way, a1 plus a2 plus a3 plus blah, blah, blah. Still going. Okay. Sometimes that shuts off on the one's listening. An expression of this form is called a series or infinite series. So what's the difference between a sequence and a series? These often get mixed up later in the semester. It's very frustrating.
Somebody's adding them up.
Yeah, adding them up. A sequence, you put commas between, it's an infinite list. A series is an infinite sum, right? So for an example, we could consider Achilles racing the tortoise. Suppose that Zeno didn't say how much faster Achilles has to be, I don't think. But suppose Achilles is twice as fast, and so he moves halfway to the finish line while the tortoise ambles forward, as they said. But now the tortoise has moved forward, so he moves half that far again to catch up with three-quarters of the way to the end. Turtle's 3/4 to the end. And then half of that, catching the tortoise, catching the tortoise, catching the tortoise. And you get this infinite sequence of numbers. That's a series. This is a particularly interesting kind of series that comes up a lot in finance and other applications. Called the geometric series, this was alluded to over there. And we'll make the following note then. A series of this form, a plus ar plus ar squared plus ar cubed and so on forever. Which, that is an example, is called a geometric series. And how might I recognize a geometric series if that's geometric, for instance?
Looking at R.
Yeah, okay, cool. You guys are kind of each term is r times its predecessor. Multiply this one by r to get this one. Multiply this one by r to get this one. Multiply by r, multiply by r. If every term is r times its predecessor, then it's a geometric series, and otherwise it's not. Not only is this an important series, it's has an easy sum, actually. So that's an example of one kind of a series. Now, how do we evaluate the sum of the series? The definition. The sum of a series, sum n equals 1 to infinity an, is computed from the sequence of partial sums. It's this sequence. S1 for the first sum is just A1. S2 is the sum of the first two terms, A1 plus A2. S3 is the sum of the first three terms, A1 plus A2 plus A3. And the nth sum Sn is the sum of the first n terms, A1 plus A2 plus dot, 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 plus An. And we call this the nth partial sum of the series. I don't know if you can't read this. I'm on kind of an angle here. You read that?
I can read it.
I hate writing these things. Okay, so it's computed from the sequence, from the sequence of partial sums as S, the sum of the series, equals the limit as n goes to infinity of the sequence of partial sums. The n term Sn. That's it. But we had to introduce sequences first, so we could define what we mean by a limit of an infinite sum, right? So we can do this last one here. Suppose I have 1/2 plus 1/4 plus 1/8 plus dot, dot, dot. Find the sum of the series of this one.
Isn't there an algebraic way to do it?
Yes, yeah, that's what we're getting. So I just thought I'd do one example first. Well, you guys are ahead of me, huh? Golly. All right. So the sum of the series, I can say this is my first term in this. By the way, didn't write it down, but the A's in the, you write it in infinite series. These are called the terms. So this is the first term. Just like in sequences, you're putting pluses between them instead of commas, but they're still called terms is the idea. Right? So I'll just put that on the side here. So An is the nth term. Right? In a series, just like An is the nth term of a sequence. It's just added instead of listed. So there's A1 and there's A2 and there's A3. And now what you need to do is come up with a formula here. S1 is the sum, is just the first term, 1/2. S2 is 1/2 plus 1/4. Right? S3 is 1/2 plus 1/4 plus 1/8. Well, it looks like these numbers are getting closer and closer to 1 maybe, because this is 1/2, this is 3/4, this is 7/8. How do I prove it? Well, I look at the formula for the nth partial sum. What is it going to be? Well, this is 1/2, the first two, the second two, the third. Sn is going to be 1/2, 1/2 squared, 1/2 cubed, plus dot, 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 1/2 to the n. Now, what's the limit of the, what's the sum of the series? It's the limit of that sequence of partial sums. The limit or the sum of the series or just write that equals is s equals the limit of this. Limit n goes to infinity of 1/2 plus 1/2 squared plus dot 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 1/2 to the n. And so I've got to figure that out. Well, I can put them over a common denominator, right? I can say this is limit n goes to infinity of 2 to the n minus 1 plus 2 to the n minus 2 plus dot 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 plus 1 all over 2 to the n. It's by algebra, right? And now what's that sum? This one maybe you know. Computer sciences comes up occasionally. What's the sum 1 plus 2 plus 4 plus 8 through 2 to the n minus 1? It's not 2 to the n plus 1, yeah.
Yeah,
Yeah, like if you add 1 through 1, 2, 4, 8 through 1,024, you get twice that, 2,096 less 1. Huh. Anyway, so yeah, all right, so that's 2 to the n minus 1 by algebraic. So this is the limit as n goes to infinity of 2 to the n minus 1 over 2 to the n. Well, you can break the limit of the difference into the difference of limits, provided they both exist, and they do, right? This over this is 1. And the other one is limit n goes to infinity of 1 over 2 to the n. Well, these denominators getting bigger and bigger without bounds, so this one is 0. And that one's 1. All right, so the limit is 1. So there's the proof that actually Achilles and the turtle cross the finish line at the same time. If the turtle starts halfway down there and Achilles runs twice as fast. But what made it difficult to understand was how can you break up things into an infinite bunch of pieces where the Achilles never catches the tortoise. Anyway. So there's a sum. Now that was kind of complicated. There's a formula that makes these easier for geometric series. Formula for these geometric series, that'll make it easier. I just wanted to display how the definition works. That one. Sn, the nth partial sum, is equal to 1 a plus ar plus ar squared plus blah, blah, blah. A times r to the n. That's the nth partial sum of the geometric series. The geometric series is a plus ar squared on forever. This is the nth partial sum, the first n terms. Right? So to compute, what's the formula for a general geometric series? And you see this one's geometric, right? Because multiply by half to get the multiply by a half to get this one by half again, by half again, by half again. So it's a geometric series. You have a general geometric series, you can do this. And now Sn plus 1. I'll just replace n by n plus 1. So it's a plus ar plus ar squared plus blah, 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 plus ar to the n plus ar to the n plus 1. Right? That's one more term. And now you can subtract these and say Sn minus, should be the other order. Sn plus 1 minus Sn. Now this one minus this one is, well, everything cancels, right? Except the last term. A times r to the n plus 1. Oh, I didn't do this right, I'm sorry. Wait a minute. I don't want Sn plus one, I want R times Sn here. And so this is equal to each of these times R, AR plus AR squared plus blah, 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 plus AR to the n plus one. And so now subtract these R Sn, the second line, minus the first line Sn is now this one. Everything cancels in the middle, all these cancel with all of them, except for this one. And this one, so you're left with this one and this one, and it's this one minus this one, so it's AR to the n plus one minus A, there we go. So you take R, the nth partial sum and R times the nth partial sum and subtract them, you get that. And now this factors, let's see, as R equivalently, R times R minus Sn times R minus one equals A times R to the n plus one minus one. And if you divide now, you get that Sn, the nth partial sum, is A times R to the n plus one minus one over R minus one, or the way it's more often written down here. This is a useful formula in itself. The sum of the first n terms in the geometric series is A times one minus R to the n plus one over one minus R, so minus the top over minus the bottom. That's worth memorizing in itself. This is used actually in calculating, in financial calculations for annuities. If you ever go into that branch, because what you get is you put money in there at the end of every month, and each month it adds like this geometric series here. But anyway, so this formula is used in finance, let's say. This was memorizing, but now what is the sum of the series? This is the nth partial sum formula, right? This isn't the sum of the series. This is nth partial sum of any geometric series. So the sum of the series, sum forever. That sounds like you're yawning. I gotta wake up. The sum of the series is then S equals the limit as n goes to infinity of the nth partial sum. A times one minus R of the n plus one over one minus R. Okay. And what's that limit? You can do it much like we did in the last example. This is limit n goes to infinity of, we can pull A out, it's just a constant. And if R, let's put it this way. Suppose R is, suppose R is greater than one, then what happens? If R is greater than one, this is driven to infinity, right? And so, and this is finite, and so what you get is an infinite result, and the limit doesn't exist. But it does not exist, because it's driven to infinity or minus infinity, actually. If R is, well, it depends on R. If R is greater than one, yeah, it's actually driven to infinity, I'm sorry. Does not exist if R is greater than one. Then you put in R less than one, and you notice that you get bigger and bigger numbers in absolute value. If you take like minus 2 to the 1, minus 2 to the 2, minus 2 to the 3, minus 2 to the 4, you get bigger and bigger numbers in absolute value oscillating between positive and negative. And again, this limit doesn't exist because you get this limit of positive, negative, bigger and bigger swings. And so if absolute value of R is bigger than 1, it doesn't exist, right? Now also you have to consider separately, what if R equals 1 and R minus 1? Well, if R equals 1, this is undefined. You've made an unjustified step back here. if R equals one, then what you're summing is one plus one, or excuse me, A plus A plus A becomes the series. This is when R equals one, you get this. And that just sums to infinity also. So if R equals one, and if R equals minus one, then you got A minus A plus A minus A. That doesn't sum to anything either, right? And so if R is greater than or equal to one in absolute value, the limit doesn't exist. But if R is less than one, then this is a trip into zero, because a number less than one taken to higher and higher powers goes to zero. And then what you get is A times one over one minus R is A over one minus R. That's this absolute value of R is less than one. And there's the result that we want. It's a theorem that we just proved. Theorem as a geometric series A plus AR plus AR squared and so on forever has some S equals that into the list. Formula we just showed S equals A over one minus R if absolute value of R is less than one, and is less than one, or does not exist. When the limit does not exist, we say the series diverges. If absolute value of R is bigger than or equal to one. So that's the big result. You can sum any geometric series very easily by just doing this. You don't have to do what we did on that first example. Let's try another one here, just real quick. Suppose I had 2/3 plus 4/15 plus 8 over 75 plus 16 over 375 plus blah, blah, blah. Is that a geometric series?
Yeah.
Yes, sir.
Yeah, it is, because I'm gonna, I'm multiplying each one times 2/5, right? So what you do is if each one is multiplied by 2/5, you say, oh, R equals 2/5. That's the multiplier. And then what's A?
It's gonna be 2/3.
Yeah, A is always the first term. So in a geometric series, you recognize it by seeing each term as just the same multiple of its predecessor, 2/5, 2/5, 2/5. That's how I know it's geometric. Once I know it's geometric, I say, well, that multiplier is R, and the first term is A, and the sum is A over one minus R by the formula, provided that R is less than one in absolute value, and it is. So this one is 2/5 over one minus 2/5. If you added those a long time on the computer, not too long actually for high-speed computers today, you get 2/5 over 3/5, you get 2/3. Yeah.
It's gonna be 2/3 on top.
Yeah, because A is 2/3.
Did I write it? Oh, I'm sorry, A is 2/3, yeah, this wrote it, thank you. Yeah, and I got 2/3 over 3/5. Is there what, 10/9? There we go. 10/9. To get 1.11111 on forever decimal if you're done on the computer. That's the geometric series there. Real short on time. I need one more example to do the interesting rest of the section. There's a great video on this. It's time to put it up. Let's just start the next one. Let's do this real briefly. There's actually only two types of series that I'm gonna ask you to find the sum of. The rest of them, what you can do is say, well, we can prove that the sum exists. Run it on the computer for a while if it converges rapidly enough. So here's the note first. Is if the limit as n goes to infinity of the nth partial sum of a series equals some number s, which is finite, a finite number. This is the sum of the series, where s is the nth partial sum. Sn is. That's how we defined it. But if the limit doesn't exist, then the series is said to diverge. So the sum of the series is S and the series is said to converge. Otherwise, whether you get infinity or you get an oscillating result, anything but a finite number for the limit, you say the series diverges. So if you get a finite number, that's the sum of the series converges. Otherwise, the series diverges.
So for like 10/9, we just say that would diverge.
10 or 9.
This is on one video.
No, I'm not sure what example you're referring to, so.
This one right here.
Oh, 10 or no, this converges, this is a finite number, so we say this converges, it's an infinite sum to this finite number 10/9. But if r is bigger than or equal to 1, then what you'll get is the limit doesn't exist. For instance, this one. Suppose I had 1 plus 1.1 plus 1.1 squared plus 1.1 cubed. This one, r equals 1.1. A equals 1, the first term. Since r is bigger than 1 in absolute value, it diverges. This is adding up bigger and bigger numbers. It's going to infinity. So you can say this sum is equal to infinity and the series diverges. Anything but a finite number, series diverges. This one here, 1 minus 1 plus 1 minus 1. This is actually a geometric series, but this applies to all series. Any series where the sequence of partial sums. The sequence of partial sums are 1, 0, 1, 0, right? First term is 1, some of the first terms is 0, some of the first 3 terms is 1, some of the first 4 terms is 0. So the sequence of partial sums is 1, 0, 1, 0, and this sequence isn't converging to any number. So we say this series diverges because here is sequence of partial sums. Does not have a limit that's invisible. So every series is the sum of the series is the limit of the sequence of partial sums. First term, some of the first 2 terms, some of the first 3 terms. To write that sequence of partial sums out, and if that approaches a number, then you say, oh, that's the sum of the series, and the series converges. But if that doesn't approach a number, even though because it goes to infinity, or it just doesn't go to anything, then you say, oh, that's the divergence. That's what you do, yeah. Good, so that's a good place to stop then, and let me give you some homework on that. Next time I have a great video, next video here. So there's a bunch of great videos. This will really teach you about infinity. Sometimes you ask this kind of question: what if I had a series A2, A4, A6? What kind of series is that? That's actually exactly the same thing we've been doing. And we can see why next time. This is still, you don't have to index 1, 2, 3, 4, 5. You can index with the even numbers, 2, 4, 6, 8. And we got to find out what kind of indices can we use. Let's see, where's my list? Look at 9.2. This is on monotone sequences. It's pretty easy, I think. 1 to 10, 17, 19, and 21. We did a couple of those. And then on beginning series, 9.3, we haven't finished this one. So skip the stuff on telescoping series. We're gonna do two kinds, geometric series and telescoping series, where we actually compute the sum. Do 1 to 14, 21, 23, and 32, but wait on telescoping series. Just do the beginning problems in the geometric series. Okay? Good, I'll take roll again next time. But I think there's got more people I have on my initial list. Okay, yeah.